Hello everyone, my name is John, and I will be telling you about this categorical semantics for probabilistic symbolic execution. I just want to start by giving some background on this term right here, probabilistic symbolic execution. So probabilistic symbolic execution is a probabilistic inference technique that's based on kind of repurposing a symbolic executor to do probabilistic inference. This was originally introduced in the software engineering community in the early 2010s, repurposing the symbolic pathfinder to do reliability analysis, and has been kind of gaining traction in the PL community recently with recent papers repurposing symbolic execution frameworks like CLE and Rosette to do probabilistic inference. The kind of idea that underlies all of these works is that there's this structural similarity between symbolic execution on the one hand and probabilistic inference on the other. So ordinarily, right, we think of symbolic execution as this procedure that takes ordinary execution and lifts it to operate on these symbolic values. And by the same token, probabilistic symbolic execution is kind of a repurposing of this inference strategy that lifts execution to operate on random variables instead. Just to give you a taste for what this looks like, here's a probabilistic program that I've written in a recently introduced probabilistic programming language called Roulette. So this is a recursive function that simulates a random walk for n steps, one-dimensional random walk. And the way you want to read this is that it kind of recursively computes a random variable. So in the base case, when the number of steps is 0, it returns this deterministic random variable at 0. And then in the inductive case, it uses this flip instruction to generate a fresh Boolean random variable to decide which direction to step in. Then based on the outcome of that fresh Boolean random variable, it uses kind of arithmetic on random variables in order to compute the result of the walk recursively. Obviously, random variables don't exist on the computer, and so what's really happening under the hood is that symbolic execution is working very hard to kind of compute symbolic representations of these random variables. In particular, all of the language constructs that are used to define this function are kind of lifted to operate on these symbolic variables, right? So this if here is not an ordinary if, it's a lifted if. These are kind of lifted integers, and these are lifted recursive procedures. Right. Okay, so for the purposes of this talk, there's a couple important points I just want to emphasize about this symbolic execution technique. So first, as you can probably already see, it's really different from ordinary execution. Okay, so with this program, you kind of have this highly non-standard reading of the program, in which everything is lifted to operate on these random variables. What this means is that it's often very tricky to reason about the precise performance characteristics of these programs, and you often need to know kind of low-level details of the implementation in order to know whether the program you've written will actually perform inference efficiently. It's often difficult to prove these implementations sound. So speaking from personal experience here, I was working on this roulette programming language I just mentioned, and even though there was kind of this existing formal framework for doing semantics of symbolic execution, we weren't able to adapt that framework to do probabilistic inference. And so what we ended up doing is kind of redoing the semantics of the underlying symbolic executor as well as the correctness proofs. Okay, so that kind of brings me to the point of this work, which is, can we introduce new semantic domains that make it easier to design, reason about, and verify these probabilistic symbolic executors? And the main idea of this work is essentially to provide a mathematical analog of a symbolic executor. Just as a symbolic executor kind of lifts all of the ordinary language constructs to operate on symbolic variables, what we want is a semantic domain that lifts all mathematical objects to operate on symbolic mathematical objects. And this is where kind of the categorical in categorical semantics comes in. So category theory is one of these tools that excels at building these non-standard models or mathematical universes. In part due to its concept of a universal construction, right? So if we look at kind of ordinary set theory, category theory provides a way of encapsulating the standard constructs of set theory in the form of abstract definitions that can be then reinterpreted in other settings. For example, the kind of standard Cartesian product of sets, function space of sets, are encapsulated categorically in this statement that the category of sets and functions is Cartesian closed. Similarly, the existence of objects like the set of lists and things like index products and coproducts correspond to certain completeness and co-completeness properties. And so what we do in this work is essentially we build multiple categories with analogous structure that provides a kind of semantic analog or symbolic analog of these set-theoretic constructions. And in doing so, we obtain a kind of symbolic set theory in which you have these same kind of set-theoretic constructions, but they have a symbolic flavor. Now, the symbolic set theory, of course, is not the ordinary set theory we're familiar with. And so inside of this kind of new universe of symbolic sets, we get access to new constructions that didn't exist before, which are particular to probabilistic symbolic execution. All of these constructions we kind of package up in what we call like a symbolic metalanguage, which can be used to quickly give symbolic semantics and prove correctness. Concretely, we build 3 new categories using kind of off-the-shelf tools from Categorical Semantics, which provide kind of concrete models of this symbolic metalanguage I just gestured at. We build a new category of symbolic sets, which I call it Czenszak, for building symbolic semantics. We build a mergeable analog of this category for talking about a technique called type-directed state merging. Then we build a category of what we call instantiation structures for proving the correctness of any of the symbolic semantics constructed in this way. Okay, so let me describe each of these kind of semantic domains in turn, starting with Czenszak. So the basic idea kind of underlying this category of symbolic sets is that it's an abstraction or axiomatization of an old kind of purely functional denotational model of symbolic execution, which was recently made precise, in which a symbolic value kind of denotes a function that's parameterized by concrete instantiations for all the symbolic variables. Let me just illustrate this with an example. So suppose I have a really simple program here. I'm just going to say let x equal the result of flip 1/2. Now operationally, what a probabilistic symbolic executor does when given this program is it just generates a fresh symbolic variable, say alpha, to represent kind of the result of that flip. But what we can do is we can think about this kind of denotationally as a function that takes in models or concrete instantiations for all the symbolic variables that have been generated so far and spits out a concrete Boolean. This function in particular is the one that's defined by cases, returning true on kind of the subspace of this space of models in which alpha holds, and returning false on the complementary subspace in which it doesn't. What's interesting about this kind of functional view of symbolic values is that these symbolic values can become more precise when they flow under different branches. For instance, suppose that I take this value x and then I perform an if on it. Then what a symbolic executor will do is it will evaluate both branches of this if, and on each branch, the symbolic value x kind of behaves as if it was either true or false. From the functional point of view, this is captured by the notion of restriction. So on the then branch, when x holds, we can think about this function x as being restricted to the blue subspace on which alpha is true, leaving behind this kind of partial function with domain alpha that's constant at true. Conversely, on the else branch, we can think about x as being restricted to the complementary orange subspace, leaving behind this partial function only defined on that subspace and constant at false. So this is kind of the key idea behind our definition of the category of symbolic sets. Basically, we take this notion of restriction and like the path-sensitive nature of symbolic values, and we axiomatize that in the form of an abstract definition. Formally, we say that a symbolic set consists of 2 things. First, an assignment from path conditions to sets which abstract over these collections of functions with domain phi. Second, for each strengthening of a path condition from, say, phi to phi prime, a function that sends these kind of abstract functions with domain phi to abstract functions with the stronger path condition. This is kind of like an abstraction of this operation of restricting a function to a smaller domain. This restriction operation is then subject to a couple of laws which ensure that it actually behaves like function restriction. In particular, if I take a function and I restrict it to its domain, that should do nothing. And if I take a function and I restrict it twice, then that should be the same as restricting by the intersection. Examples of symbolic sets include, of course, functions with the right domain, but also many other things, such as formulas with the restriction operation defined by a conjunction, and also stores defined as mappings from variables to formulas, with the restriction operation kind of defined variable by variable. Now, what makes this definition categorical is that that elementary definition I just showed you can actually be repackaged in the form of a functoriality condition. So if we think about like a picture of a symbolic set, you can see that it kind of defines a mapping from path conditions to sets. So for each path condition phi, you get a set hat x sub phi. And for each strengthening of a path condition from phi to phi prime, you get a function from x sub phi to x sub phi prime. We can make this precise by taking all the path conditions and packaging them up into a category that we call P. Then we can redefine symbolic sets to just be a functor from this category P to the category of sets. The assignment from phi to x sub phi then becomes the action of this functor on objects. The restriction map becomes the action on morphisms. And these laws that I stated earlier become the functoriality laws. The advantage of this kind of crisper, more abstract definition is that it immediately places symbolic sets in the context of a whole category of symbolic sets, namely the category of functors from this category P to set. Now we're really off to the races because this category is a well-known form of category called the category of presheaves. That makes this category of symbolic sets that we've introduced an instance of a well-established recipe in categorical logic called presheaf semantics. Many books have been written already on presheaf semantics, and so we're basically allowed to kind of import all of that machinery wholesale to kind of complete our universe of symbolic sets with a rich collection of universal constructions. Concretely, we kind of obtained this symbolic metalanguage that I was gesturing at earlier, which includes features like simply typed lambda calculus, algebraic data types with pattern matching, and monadic do notation for working with these special monads that we introduced for symbolic execution. The result is that we can essentially take simple type theory as a metalanguage for building symbolic semantics. For example, suppose we want to make a probabilistic symbolic executor for this imperative language. What we can do is we can first write a monadic definitional interpreter for this language, which just looks like an ordinary interpreter. In particular, the interpretation of sequencing can be given by ordinary monadic bind, and the interpretation of if can be given by ordinary if. But then what we do is, rather than reading this interpreter in the normal way, we're going to reinterpret this interpreter in the category of symbolic sets that we just constructed. Once we do that and unfold all of the definitions, out comes a symbolic semantics that captures kind of all the details of symbolic execution that we would need to do to perform probabilistic inference on this language. In particular, if we kind of quickly zoom in on the semantics of if here, you can see that the symbolic semantics computed in this way tells you that you have to maintain a path condition, and then to symbolically evaluate the if, you should evaluate the guard to get a formula, conjoin that formula onto the path condition used to evaluate the branches, and then combine the results of evaluating those branches. In fact, this definition contains enough operational detail that you can essentially just transcribe it into code. So here I've just taken that math on the previous slide, and I've turned it into a Haskell interpreter that actually does perform probabilistic symbolic execution for the imperative language I showed earlier. Okay, so just summing up here, we've introduced this category of symbolic sets, which is kind of like a lifted set theory that is a nice home for symbolic semantics. And we introduced a metalanguage that allows us to take definitional interpreters and automatically get symbolic semantics for a language of interest. Finally, the symbolic semantics that we get out, even though they're denotational, are kind of informative and executable. They contain enough detail to be turned into reference interpreters. Okay. The second thing I want to talk about is that we also introduced a category for talking about a technique in symbolic execution called state merging. This category we call the category of mergeable symbolic sets. To give some context for state merging, I want to just consider this simple program here. So this program takes a flip and it does something rather unusual with it, which is that it branches on there, and then in each branch it just returns that variable unchanged. Okay, so based on what we know about symbolic execution, this program will turn the flip into a symbolic value, which kind of represents this function that we saw earlier. Then, symbolically executing the if will restrict this function to the blue and orange subspaces on both branches, leaving behind these kind of partial functions. Now, a traditional symbolic executor would kind of continue to evaluate both branches, leading to a duplication of work. And so the purpose of state merging is to take these two values and combine them into a single value, intuitively performing the union of functions, leaving behind a single function that summarizes the result of both branches. So once again, what we do is we axiomatize this kind of abstract operation of union providing a mergeable analog of symbolic sets. So whereas symbolic sets kind of axiomatize this restriction operation on functions, our category of mergeable symbolic sets axiomatizes this operation of disjoint union. And again, we kind of make contact with categorical machinery here. In this case, we use this idea that the union operation, like this equation that goes from a combination of functions defined on subspaces to a function defined on the whole space, is kind of like a passage from like a local function to a global function. This function defined on the blue subspace is local to the subspace alpha, function on the orange subspace local to its complement, and then the merge kind of amalgamates these into a global operation. It turns out that topologists have thought very hard about this kind of passage from local to global. And so we're actually able to reuse this abstract concept of sheaf in this context to capture the notion of state merging. Starting from this intuition, we kind of build this like dictionary between symbolic execution and sheaf theory. The kind of space of models that I've been drawing as a picture corresponds to what is traditionally a topological space. Path conditions correspond to open subspaces, and this merge operation corresponds to the amalgamation operation that turns out to be key to defining the notion of sheaf. Formally, we can define the category of symbolic sets to be this subcategory of SymSet consisting of those pre-sheaves that are sheaves. This makes mergeable symbolic sets an instance of what is known as sheaf semantics, which, like pre-sheaf semantics, also kind of has received extensive treatment. And so just like with the category of symbolic sets, we obtain a kind of mergeable analog of our symbolic set theory that automatically understands state merging. In particular, if we take this definitional interpreter for our imperative language from earlier, and we reinterpret it in the category of mergeable symbolic sets, then we automatically attain a symbolic semantics with state merging. Zooming in on if, for example, you can see that the semantics of the symbolic if is going to take the stores produced by both branches, and it's going to use this square cup operation to combine them. This merge operation is defined not uniformly, but rather in a type-directed manner, which can be calculated from the universal constructions that are available in the category of sheaves. For example, if we look at a collection of merge operations for different types, you can see that the merge operation for the singleton symbolic set is defined to return the singleton element. Merge operation on formulas is defined in the usual way, and the merge operation on pairs is defined pointwise. What I find especially nice about this is that the kind of sheaf theory provides an abstract characterization of many real implementation details. For example, suppose we want to calculate the merge operation on lists. It turns out that if you take the formula for computing list objects in a category of sheaves, and you unfold all the definitions, you get this merge operation, which says that lists should be merged by length, which turns out to be exactly how state-of-the-art implementation like Rosette merges lists. Okay, so just take a stock here. We kind of made contact with sheaf semantics, and that allowed us to give a denotational explanation of real state merging code alongside this kind of topological perspective on symbolic execution with state merging. All right. I just want to quickly talk about the final part of what we did, which is we introduced a new semantic domain for talking about correctness. So this semantic domain is an instance of the same recipe I've been describing so far. We took a kind of classic definition of correctness, which says that a symbolic execution should simultaneously simulate the results of ordinary execution on all instantiations for symbolic variables, and we abstracted it to work in the categorical context. For this abstraction, the key thing is to note that whereas ordinary execution runs one input at a time, symbolic execution runs simultaneously many inputs parameterized by a model M for all of the symbolic variables. Now, in order to specify correctness for the symbolic semantics, the key thing to formalize is this notion of instantiation, what it means to take a symbolic value and specialize it against a concrete model. And so just as the categories of symbolic sets and mergeable symbolic sets axiomatize restriction and union of functions, we introduce this third category of instantiation structures that axiomatizes function application. It turns out that, once again, we have the ability to use categorical machinery in this context, whereas symbolic sets and their mergeable counterpart correspond to pre-sheaves and sheaves. This category of instantiation structures corresponds to a technique called gluing, which you may have heard in the previous talk in the form of proof-relevant logical relations. Using this, we give a model of symbolic set theory that understands this notion of instantiation and prove a general theorem that says that any definitional interpreter written using the symbolic metalanguage is automatically correct. And I want to emphasize that this theorem works no matter whether the semantics is using state merging or not, and it generalizes to the probabilistic context, and it makes use of a kind of compositional notion of correctness. Okay, there's more details in the paper, which I invite you to check out if you're interested. And I just want to quickly say that in future and ongoing work, we're thinking about trying to mechanize a lot of these things in a proof assistant to make them a bit more accessible, and also to try and connect the abstract theory we've developed to low-level implementations. Okay, that's all I have.
We have time for 1 or 2 questions.
Thanks for your talk. I'm just curious how this would work with like equivalence. So like maybe let's say you have 2 programs which are like have the same expected value, have the same like distribution of outputs, I guess. Would they have the same categorical semantics, or like to what extent would they be the same?
Yeah, that's a good question. The symbolic semantics that you get kind of captures the behavior of an implementation. So there are going to be certain programs whose symbolic semantics will differ because their symbolic execution will differ. So for example, you could have one program that computes a distribution using 2 flips and another computes the same distribution using 3. Those will have different symbolic semantics. But you will be able to prove, using our framework for correctness, that both of those symbolic semantics kind of refine the same distribution, or ground truth semantics.
Can you replace set with something else?
Yes, yes you can. The framework is quite general, and you can replace set with
relation.
It would have to be a category that satisfies certain universal properties which I don't have the list of on hand, but yes, you could.
Okay, thanks.
Yeah.
All right, if there are no more questions, let's thank John again.